Okay, the next section that I wanted to talk about is aerosols. And aerosols can be detected by direct reading instrumentation by really two major mechanisms. The first is light scattering, and the second is by alpha absorption. And let's go to look at an aerosol photometer. This is one by Tech Services. And it's a direct reading aerosol photometer, and it works by one of the methods that I'll be talking about in just a second. But basically what it will do is go into an area where there's particulate matter or aerosols present and give you a direct reading on what the concentration of those aerosols are in that particular environment. The light scattering works by taking advantage of the fact that particulate matter is going to scatter light. So over on the left, you see if we have light that's going through a beam that's being directed in one area where there's no aerosols that can reflect or scatter the light, all the light that starts on one end is going to be transmitted to the other end, and none is going to go over here to this green transmitter down on the bottom. Now, alternatively, if you have a dusty environment where there's lots of particulate matter and you shine a light beam from one end of the area to the next, some of that light is going to hit the particulate matter and cause it to scatter. This would be like taking a flashlight and shining it through a dusty room, driving at night during a snowstorm, where you will see reflections of the light where it's being scattered. And what will happen is that less light is being transmitted from one end of the beam to the second, and some of that light is being scattered over to the plate here. It's red, where you can actually measure it. So with light scattering, you can measure the amount of aerosols that are being scattered in any kind of medium. And the dustier it is, the more light that will be scattered. And so you can relate the amount of light transmission to the aerosol content of the air. So it's a real simple principle, and it's based upon the fact that particulate matter is going to scatter light. Another way that aerosols can be measured by direct reading instrumentation is illustrated here. This is where aerosols are going to be measured by seeing their ability to scatter a alpha source of radiation. Down at the bottom we have an americium source, and what it's doing is putting out alpha particles from one end of the chamber to the other chamber. Now, if there's no particulate matter present in the chamber, they can go from the plus charge plate to the negative charge plate to the plus charge plate, and everything will be fine in terms of the way the circuit is set up. However, if there's any particulate matter, alpha, which is, as we'll talk about in a couple of weeks, a helium nucleus with 2 protons and 2 neutrons, is a large matter, and it can hit the particulate matter and scatter. And when that happens, the current that's supposed to be going across those metal plates won't be, and that will trip a circuit and set off an alarm. And this is typically how smoke alarms work. If you have a smoke alarm in your house, what you are probably using is an americium source that's putting out alpha particles. And if there's any smoke particles that come in present in that chamber, it's going to scatter the alpha particles, disrupt the circuit, and that'll be tied in the case of the one in my house, to I think 120 or 140 decibel alarm that will alert me to the fact that particulate matter is in that ionization chamber, i.e. there's a fire and there's smoke particles present. So this is an application of a direct reading instrument. Now the next area that I wanted to talk about as I finish this up isn't really direct reading, but it gets into another type of sampling before we get into more specific aerosol sampling in our next lecture. And this is extractive sampling. Now, extractive sampling can be done 2 different ways. The first is an active sampling mechanism, which is where you use a pump, a collection device, and then do some type of analysis later. And the second is a passive sampling technique, and by passive sampling, you're relying on passive diffusion. So this uses diffusion, a collection device, and some type of analysis later. This is a typical sampling tray, and this is a picture of one that's being calibrated, but this has a pump, some Tygon tubing, and some kind of a filter. And what you do is you'll be pulling air through that filter. The calibration is done before and after the air sampling to make sure that your pump is pumping at the end of the shift what it started at the beginning of the shift, and if not, you need to make the necessary adjustments. But this sets up how a active sampling is structured. You have a pump which is pulling air through some kind of a filter, and you know the quantity of air. And so if you can collect some material on the filter, you have a weight of the material on the filter, you know how many cubic meters of air have gone through your pump, and so you can represent your results in terms of milligrams per cubic meter, which is one of the ways that we talked about expressing results earlier in the semester. If you're collecting for a gas or a vapor, you typically use some kind of a sorbent tube. This is an example of a sorbent tube here. How it will work is one end will be open to the environment, the other end will be attached to your Tygon tubing. You'll be pulling the contaminated air through the sorbent tube, and at the end of the time that you're pulling the air through, whether this is a 8-hour shift or longer, you'll take the sorbent tube off, cap the ends, and send it to the laboratory for further analysis. And some of the analysis they'll do is, as I talked about last week, they may extract the contaminant with certain solvents and inject it on a gas chromatograph and analyze it by electron captured detection or mass spectroscopy or some other detection method. But this is a common sorbent tube for collecting some type of a gas or a vapor. This is a more specific one. This is a picture of the one I was talking about last week, the OSHA Versatile Sampler. And this can collect a variety of different types of organics, but it works the same way as the previous sorbent tube. You're going to have one end where you're attached to your Tygon tubing, the other end that's open to the environment. At the end of your collection time, you'll put the caps back on and send it to the laboratory, and they will extract whatever you've collected on the sorbent layer and be able to identify how much material has been collected in that tube. And again, you can represent your results in terms of milligrams per cubic meter. Now this is passive sampling. With passive sampling, you don't have a pump. And there are some advantage to that because a lot of workers don't want to have to wear a pump around on their belt for an 8-hour shift and are more receptive to wearing a passive sampler that they can clip on their lapel or on their belt or somewhere else that is not going to be quite as cumbersome during the workday. And this is an example of a couple different types. The one on the left is an organic vapor sampler. The one in the middle will sample for inorganic mercury vapors, and the one on the far right can sample for aldehydes. So you can get these for a variety of different types of applications. This is an SKC sampler. This is a passive sampler. It works just like any of the ones that I showed you on the previous page. But what they all have is some kind of a sorbent that's present. The gas or vapor can pass through this diffusion barrier, and it will be trapped on the sorbent, and you can collect a certain amount of material and correlate it to the amount of time that the worker was wearing it. So again, you can get a determination of concentration based upon this. And you can buy this particular type from SKC, and we'll click on the SKC website really quickly. It's a good website to look for a lot of your industrial hygiene equipment that you'll find for your cost analysis. And this gives, again, this is the picture I just showed you. It's a cross-sectional view of the SKC 575 series passive sampler. And again, there's small badges that individuals can simply wear, and you can determine what the concentrations may be. There's some nice things about them that are listed here: in accuracy, economy, they don't cost that much, they're very efficient, etc. Now another type of sampling that's reasonably new, which is a very effective modern technique, is helium diffusion sampling. And with helium diffusion sampling, you will collect samples in a personal monitoring canister, and you can buy these canisters of different size. And the way that these work is they're based upon the fact that helium has a higher diffusion rate relative to that of air. So you don't have to go through calibrations because these are basically calibrated before you use them. And they're highly reproducible, technically much less challenging of a method. And here's some pictures of a helium diffusion sampler. Basically, you'll open these up and have them open over the course of a shift, cap them, and you can determine the concentration of what's been collected. I'll go to the website for the ones that are vending these, but again, these are pictures of 15-minute, an hour, and 8-hour type of sampling. These are personal samplers that are very, very small. You can collect, these have different collection times on them. And there are some real advantages to using these in terms of technical ease of use as well as reproducibility. And again, it's based upon the flow rates being controlled by the diffusion rates for helium. So calibration is real simple on these. And another method is impingers. These are liquid impingers, and you can get aerosol impingers as well. And impingers will work by bubbling dirty air through some kind of a solvent, and the solvent will collect the contaminants, and clean air will go out the other side of the impinger. I'm going to go to the SKC website again and have a little bit more information about different impingers. This is midget impingers. And you can buy these for a lot of different air sampling applications. But what they're going to be doing is trapping the contaminant of interest within the impinger, and so you can measure it later. Now, these can again be used for different gases and vapors. If one application is in law of enforcement, if you've ever heard of the breathalyzer test, what you're using is an application of an impinger where you'll blow into some kind of a tube where there'll be a material that can trap any ethanol, and usually it's potassium permanganate or some other kind of solution that can oxidize the potassium permanganate, and so you will then be able to have a colorimetric change and relate that back to the ethanol concentration. So ethanol is a solvent. You can use this technique for breathalyzing, as well as sampling for many different types of organics or other compounds that are common contaminants in air. You can also use it for aerosols, because dirty air is going to stay behind in the aerosols, and this technology has been in use before the Gauley Bridge disaster. There were impingers that were available to bubble dirty air that contained dust into these impingers, and once you're finished with your collection, then you can take aliquots of the air and put it on a microscope and count the particles. And the old days of industrial hygiene, they used to do just that. They would collect dirty air through water, take aliquots of the water, put it on a microscope on a grid, and count how many particulates there were present based upon the volume of air that went through. And you would see expressions of particulates per so many cubic feet of air. This is the same principle that a Rainbow vacuum cleaner works with. I have 3 dogs, and they stay in the house a lot, and we use a Rainbow vacuum cleaner because it will take and pull dirty air through water, and the dirt stay behind in the water, and clean air will come out the other side. So impingers can be used for industrial hygiene sampling. They can be used for many applications, including environmental cleanup of contaminated air. And that concludes the discussion of direct reading instruments, as well as a little bit on extractive and active and passive sampling.